All right, take 4. All right. This is at the bottom of, not quite at the bottom, but pretty close to the bottom of my bookshelves. Not on the bottom where I never get things, but down pretty low where it's hard to just pick something up. So this is the book that I want to talk about today by Yakir, Aharonov and Daniel Rohrlich. It's Quantum Paradoxes, Quantum Theory for the Perplexed. Back when Randy and I first started podcasting in 2014 or whatever, this was the book that we used. We were going through this book chapter by chapter. So it's a very nice book. I originally picked this book up because I was teaching modern physics at the time, and I wanted to find something that would be really useful to help introduce things, right? To talk about what's going on in quantum mechanics. I was hoping this would work out. It's a little too complicated, but it has a lot of really good stories. So it doesn't have a lot of things that you could pull into your standard modern physics class, but it does have a lot of things that you can talk about in the class a little less quantitatively than this book actually works with. So this particular book suggests it to be a supplementary material for quantum mechanics class, maybe your standard junior level quantum mechanics class. And it has its own way of going through things, which is to go through each chapter in a fairly normal way and introduce each topic with a paradox and try to resolve the paradox, show that the paradox is only a paradox of your understanding, not a paradox of real Aristotle quality, right? So that's what we wanted to look at in this thing. So the entire book, actually, and I didn't really feel this when I first started reading it, but when I got a little farther through, the entire book is actually a little bit closer to an argument for Aharonov's own interpretation of what's going on with quantum mechanics. And so, like we said previously in our things, when people do these kinds of reviews, they go to the table of contents and talk about them, right? So the introduction is just talking about paradoxes and the different things that could sort of count as resolutions, right? You can have errors, you can have gaps, you can have contradictions. When we find a paradox in physics, what we really want is a contradiction. A lot of the things that we talk about as a paradox would be a error, like when you talk about the twin paradox in special relativity. That is an error. That's not a real paradox. It doesn't give you a contradiction between two different theories. If you can get a contradiction between two different theories, what you get is something that can lead you to new physics, something that can help you make a better physics. All right. And then we start off with how to weigh quantum. And that's just talking a little bit about quantum, quanta and uncertainty relations, and you get the clock in the box paradox. I probably should not go through all of these, especially since I haven't read this for a long time. I have read it many times. I read it before we did our previous here we go. We did our previous podcast, and then I read it several times. Once when we started the podcast up again, once before each podcast thing, once when we started the podcast, once when we started up again, and possibly even a fourth time I went through it, when we were thinking about finishing up. We only got about halfway through this, because it is a textbook. So this is Bohr's representation of Einstein's clock in the box paradox. And this is sort of representational. The sort of things that Einstein would do is he'd find something like this very complicated system. And he'd say, okay, well, if something happens here, we can't believe that something else would actually happen. Bohr would then come through in all of these debates, and he'd say, okay, well, actually, if you're very, very careful, with the quantum mechanics. You make sure everything is described by quantum mechanics. Everything is perfectly fine. So, the problem that Einstein posed here was something like, oh, well, I can't remember it well enough, so we'll have to go back. Nice color pictures. All right, so that was sort of showing things like that. I should probably, if I was going to talk about a paradox, go with chapter 3, where they're really starting what's going on in the book. And you can see he starts with the paradox, and talks about the EPR paradox, the Einstein-Podolsky-Rosen paradox, which turned into Bell's theorem, and actually shows that you have to interpret the probability in quantum theory differently than in regular stuff. That the quantum probabilities are important. The way you generate those probabilities are true, even though it seems like you're getting different kinds of paradoxes from the point of view of regular probability theory. But probabilities in quantum mechanics, of course, are generated through wave functions, which are, in a way, not quite the square root of the probabilities. So take those wave functions, you take their square, and you get the probability density function over space, or maybe over time, depending on what you're doing. All right, phases and gauges is two procedures, but this brings us to the Aharonov effect. And basically, this means that this phase, you get this phase in your wave function, is a real thing. So you think this is just a gauge transformation, that it doesn't show up in anything. But the Aharonov effect, that basically showed that, at least in principle, there are physical things going on with that, physical things going on in that phase. You could measure it if you were very, very clever. Then he talks about modular variables. This is very interesting. I'm not sure exactly why they're so necessary, but Aharonov seems to take the position that something like the like a diffraction grating is a more fundamental measurement in quantum mechanics than the double slit experiment. So we're all used to talking about the double slit experiment for a couple of reasons. One, it's very easy to set up, and two, it showed that light was a wave. That was the original way to show that. And it has some very interesting things. So you can even get, fairly large biomolecules to show interference in a similar sort of experimental setup. But Aharonov wants to use these modular variables, which are basically saying that every, say, distance between wires in a diffraction grating is a modular variable, right? Is the same thing. So if you have a distance d between these things, and you're at the position x in between them, it doesn't matter if you're at n dx or n plus 1 dx, n d plus x or n plus 1 times d plus x. Those two spots, because they're in the same relative position in that slot between those two wires in the diffraction grating, they are functionally equivalent. And through this, he creates something like is it in here? Well, he's got the x mod, p mod representation. I think that it's in this chapter that he talks about a more general uncertainty principle based on those modular variables. Non-locality and causality. It's trying to talk about causality in a piston. That's going to be your non-locality and causality. Actually, he's going to talk a lot about this sort of stuff. These these things actually contradict with each other, and so you want to find a way to bring them back together, because we don't like either of those. The EPR paradox told us that we had to get rid of non-locality or causality or quantum mechanics. The aspect experiment and later experiments that keep going on say you can't get rid of quantum mechanics. So you either have to get rid of locality or locality or causality. And nobody wants to get rid of both of those things. So how can you fix that? That's part of what that's talking about. And then he talks about quantum measurements, quantum measurement theory. That's very important. And measurement and compensation. Again, this is more measurement stuff. You have to understand how measurements are made. You have to have a model for how measurements are made to understand quantum mechanics. There are basically two parts to quantum mechanics. One is the evolution of the wave function, and the second is how you actually get some sort of a measurement from it, right? So that measurement theory is incredibly important. You can go back to von Neumann. You can talk about the Born rule, all that other stuff, but it's all very important. It's the reason why, because the measurement and the evolution of the wave function don't really reconcile very well. That's where a lot of these paradoxes come from. Quantum cats basically talks about Schrodinger's cat and the interpretations of quantum mechanics. So this is sort of the middle of the book, and this first part has been sort of just talking about quantum mechanics and how Aharonov likes to talk about it. But he's been looking at it this way because after he goes through quantum cats, we're going to start talking about, start building up his own interpretation of quantum mechanics. Okay. Then a quantum arrow of time. So trying to talk about boundary conditions on the universe. This is basically the way he's interpreting quantum mechanics, or his boundary conditions on your wave function. Super selection rules for different states. Quantum slow dance. And talking about path integrals and adiabatic approximations. You can see that. Charge and fluxons, and I have to admit, I completely forgot about that. The Berry phase, that is not a phase. When I first encountered the Berry phase somewhere, I think it was when I was looking into the quantum Hall effect. I was very confused because I'm looking into the quantum Hall effect because I'm interested in condensed matter. And so when you use phase in condensed matter, it's usually talking about a phase of matter. And it was everything that we were trying to say about it was just uninterpretable because it relates just the phase of the wave function. So it's very important, that phase of the wave function and how it accumulates, right? How that phase accumulates. Quantum measurements and relativity. This is important. This is actually something that Aharonov goes into a lot, and I didn't mention it previously, is that many of the standard techniques in a quantum mechanics class, many of the standard things you'll look at, like a Gaussian wave packet, can't work, right? Because of relativity. The Gaussian wave packet is meaningless because of relativity, right? So you have to have a more constrained version of that Gaussian wave packet. And he talks about exactly how to do that. How to observe a quantum wave. And this has the dipole paradox. And here we're moving towards quantum field theory. So we were talking about Feynman just a second ago. Where was it? Feynman paths. So we're still moving towards quantum field theory, but we've started a couple of chapters previously. Weak values, weak measurements. Weak measurements are very important, very interesting, because they sort of show you what is really going on. So, or at least that's an interpretation of some people like Aharonov. Weak values and entanglement, a way to sort of understand what weak values are, and then finally wraps everything up in the quantum world, what he actually thinks of as quantum mechanics, right? Causality and non-locality as axioms and so on. All right, so that doesn't really explain anything because we didn't quite talk about it. So I started talking about it a little bit when we talked about these things, boundary conditions on the universe, but those keep coming back over and over and over in this book. How the boundary conditions on the wave function influence the interpretation. That, and we talked a little bit about relativity right over here, over and over and over again. The boundary conditions are really mostly the second half of the book, but relativity is all over. So, I mean, the book has a lot of different things in here. Here you've got a Stern-Gerlach experiment inside of a rocket ship. Very interesting. That's for your super selection rules. Right? Everything is relative. And it has real problems. This is not a book for the faint of heart. So this is not a book that's going to... this is a book that's going to make you work to understand it, right? And this is actually something I should probably do. So I've always meant to go through this. I did go through Sakurai a couple of summers ago. I don't have a full summer again this semester, but maybe next summer or the summer after that I can get back on this because it looks more and more interesting the more and more I do the show. So the deeper and deeper we get, the more interesting these things become. I think part of that is just because in this book, Aharonov and Rohrlich really do take relativity seriously when they're trying to interpret quantum mechanics. A lot of the interpretations of quantum mechanics really don't. A lot of the time when people are interpreting quantum mechanics, they're pretending like you have a flat space-time. You're pretending like signals can travel faster than light. And that's not really true, right? Maybe it's a little bit true, but only on the outside. And so, I found this a very interesting book. I liked it very much, and I still like it. And I think probably you'd like it too if you wanted to take the time to read through it. Again, it is highly mathematical. It has... Actually, that looks fairly simple. Yeah, I mean, that looks like standard quantum mechanics. Let me see. Okay, I'm not finding it. But the reason why... Okay, here we're getting into some weird things where it's very important to understand and keep track of all of these different operators. The reason why we didn't get through this is because Randy was getting a little bit anxious about all the math in the book, because it really is a junior, senior level science book, right? You really have to be able to read the math for its physical insights, right? Which is kind of hard if you're not used to it. And it's kind of hard if you're getting new math. And some of this is math that Aharonov and Rohrlich are making up, right? So not necessarily for this, in previous sort of papers and things, but, if you're not used to that, it's very, very difficult to look at a piece of math like that and say, well, what are all of these things? Why are there so many dots? Probably that's not a big thing for you, but for a lot of people it would be. Why are there R's with one dot and two dots and different R's? Well, maybe different R's mean similar things. And what's all this other stuff? What's this time? Why do we have a times here and just things multiplied by each other there? I mean, it is a science book, so if you have the background, I think it's a very useful book, but I think that you probably do need to understand differential equations before you can go through this book. So again, I love the book, but it is a complicated one. All right. So anyways, thank you very much for listening. Great book. Like it a lot. I wish we'd finished this. I liked our old format quite a bit and where we went chapter by chapter through a science book. So that'll do it. This is a little bit longer because I deleted a bunch of things off of my phone, but I'm still running out of time on my little phone recording device. Bye now.